All right, good morning, good afternoon, good evening, whenever you're watching this video. What we're going to be talking about today are segment lengths within circles. Okay, now we've been concentrating so far on angle measurements within circles. Now we're going to take a look at how the segment lengths, the chord lengths within the circles play out. And so in order to do that, we have this theorem 1112 that we're going to take a look at. All right, in theorem 1112, I would like you to go ahead and draw. Actually, there's three parts, so we'll say part one. Okay, go ahead and draw a circle with, it doesn't matter where the intersection takes place, kind of like the first part of theorem 1111. And let's go ahead and do this. Let's label this A, B, C, D, and E. Okay, and in order to figure out these segment lengths, how they are going to play out within the triangle, within the circles here, I'm going to go ahead and make them into triangles. So go ahead and mark your paper like that. Now, what I notice about these two triangles as we start out is that the vertical angles are congruent. So I'm going to mark those two angles congruent there. I also notice that this inscribed angle here at C intercepts this arc here. And I notice that this inscribed angle at E intercepts the exact same arc. So angle C and angle E intercept arc AD. And we talked earlier that those two inscribed angles would then have to be congruent to each other because they intercept the exact same arc. Okay? Now, as I look up there and look at that picture, I see that I have two triangles that are similar by angle-angle. For example, I could write down triangle ABC is similar to triangle DBE by angle-angle similarity. Okay? Now, because of the angle-angle similarity, I can then set up a proportion that would deal with the sides of the triangle. Now, remember, we want to look at the side lengths that are present within the circle right here. So I'm looking at this side length here and that one there and this side length here and this one here. Okay? And so what proportion could I use to set up to solve for that? Well, I can go ahead and take AB is to BC. Okay, this length is to this length as looking at the other side, AB corresponds with DB is to BE. Again, BC and BE, they correspond to each other. All right, now your textbook actually takes it a step further and shows the next part of the equation, which is actually, I think, is easier to understand. And so if we cross multiply here, we get AB times BE will equal BC times DB. Now, the reason why I wrote that out, like I said, I think it's easier to understand, and here's why. If we draw a circle, and we can start out the same way as we did before, I could label this A, B, C, and D. If I use the segments that are current within the picture up here, starting with AB, I have A times, and it says BE down here. So BE is over here, B. Now notice those are the two segments that are along the same chord. Okay? And then we go BC, well that's this segment here, that would be C times DB, which is D. Okay? So it's the two portions of the chord, or the product would be equal to the two portions of the chord. And so this is the formula that you're going to be using for part one of theorem 1112. Now, like I said before, there are actually two parts of the theorem that we're going to be looking at. So let's look at part two here real quickly. Part two, okay, and here's what part two looks like. If we have an intersection outside the circle, okay, just like in theorem 1111, the intersection's inside the circle, there's a certain characteristic that takes place. This is outside the circle now. And I'm going to go ahead and label my parts like this: A, B, C, D, and E. Okay? Now, because I want to look at these lengths that are going to occur because of the circle and the intersections with the circle, I am going to go ahead and connect those segments, forming the two triangles that are present there. All right. Now, if I was to separate the two triangles, we would know that angle C, okay, maybe I should do this before I get going here so everybody can see everything. What we're looking at, the two triangles, when I say this, would be this triangle here and then this triangle here. Okay, so as we look at that, you can see that angle C is in both triangles. So, angle C is congruent to itself. As far as any other parts of the two triangles being congruent, well, what I know is that angle E here, this inscribed angle, is half of arc BD. And I also know that angle A over here is half of arc BD as well. So as a result, those two angles, as we've talked earlier, have to be the exact same measure as well. Now, if that's the case, triangle ADC would have to be congruent to triangle EBC, again by angle-angle similarity. Okay? So as a result, if we are looking specifically at the lengths of the triangle, now maybe what I should do, I don't know if it's possible to get rid of that stuff. I may have to go ahead and clear some things off here. Okay, so we've already proven the triangle's congruent by angle-angle. Okay? Again, let me write that down. ADC is not congruent. Why did I write congruent? Did I write congruent on the last one? Oh, thank goodness. All right. ADC is similar to triangle EBC. Okay? Again, this is by angle-angle similarity. So what we want to look at now between these two triangles here is the relationship of side lengths that we're looking at. Okay? And we're specifically looking at, and I can highlight this length right here and this length right there. Okay? So if I look at this triangle down here, ADC, which two segments are present within that segment right there? Well, I've got AC, okay, that whole segment there, and DC, both coming from this triangle, AC and DC. In the other triangle, the corresponding side lengths of AC would be EC, and the corresponding segments of DC would be BC. Okay? Now again, I'm going to cross multiply like we did the last time because I think it's easier in the end to see what's going on here. And if we cross multiply here, we get EC times DC will be equal to AC times BC. Okay, the products there. Now, I know that looks like a lot of letters. Let's simplify things a little bit. And if I were to go ahead and redraw what we have here, okay, basically what we're looking at, EC is the entire length here, and we have DC, which is just the portion on the outside. So if I were to go ahead and do this, label this whole length X, and then this length Y, okay? And then for the other one, AC is the whole length, so we'll label this whole length Z, and then this length right here, I'll label as A. If we go ahead and take the whole length of the secant ray and multiply that by the portion of the secant ray that's outside the circle, that will equal the whole length of the secant ray times the outside portion of the ray that's outside the circle. Okay? And so again, that's the formula we're going to be using for part 2 of Theorem 1112. The last part of the theorem, the part 3, looks something like this. Okay? You have a circle, you have a tangent line to that circle, and then it intersects the circle in some way as a secant. Okay? And so what we're looking at here, if I was to label this A, B, C, and D, okay, there's a relationship between this segment here and actually all three of these segments here, 1, 2, and then 3. There's a relationship there that we want to look at. And so what I'm going to do is I'm going to actually highlight this right here. Make that triangle and make that triangle there, okay? Now, notice here that if we are looking, and let me highlight the two triangles that we're going to be looking at. We're going to be looking at this triangle here. Oh, undo that. I meant to go here. This triangle here, we're going to be looking at this one, and we're going to be looking at this one here. Okay? And so those are the two triangles that we want to be concentrating our eyes on. Now I'm not going to leave them highlighted here because I want to make some other marks and I don't have to go ahead and erase them later on. So looking at what we have now, what I'm going to do, I know that C was in both of those triangles that I just showed you. Okay? So keep that in mind. I also know that this inscribed angle at A comes out and intercepts arc BD. And this tangent line with this chord also intercepts arc BD. Now, I know you guys are good with the inscribed angle and the intercepted arc, the angle's half as much, okay? The one that we haven't practiced a whole lot of is the tangent line of the circle with the chord. If it intercepts an arc, it's also half as much, okay? So make sure you understand that's the exact same concept. So I know that this angle and this angle have to be the exact same because they intercept the same arcs. Now from there, I can then prove that our triangles are similar again by angle-angle similarity. So I'm going to do something like this. Let's do triangle ADC is similar to triangle ADC. That would be DBC. Okay, again, angle-angle similarity. Okay. Now because of that, we can set up some proportions, and we're going to focus primarily on this segment here and any segment that would be up here, okay? And so what I'm going to do, I have triangle ADC. If I focus on what we have AC and we have DC. Those are the two segments that we originally had there, okay? Now the corresponding segments to AC would be DC. Good, that's one of our segments. And the corresponding segment to DC would be BC, also one of our original segments. Okay. Now I'm going to cross multiply. AC times BC is equal to DC times DC. Now I'm going to simplify that up a little bit. Anything times itself is going to be the square of that value. So DC squared. And so this is the formula we're going to be using. Now again, to simplify things, if you want to, I'm going to label this X. That's from here to here. I'm going to label this Y. And I'm going to label this Z. Okay? And so down here, DC, that's squared. So X squared will equal AC times BC. AC is the entire length here, which is Z. And BC is the outer portion of that secant ray, which is Y. Okay? So again, this is the formula I want you using when it comes to the problems for tonight. So, taking a look at the worksheet here, let me make it bigger so we can see everything. You'll notice Theorem 1112, you've got all the formulas set out for you right there. Okay? Now, if you go back to my original proof right here, I use just X times Y, the whole length, times the outer part is equal to Z times A, the whole length times the outer part. If you go to this one, it says the outer part times the whole length. It's just using the summation right there. So that's the only difference between what I showed you and the actual equation within the theorem. So as we look here, maybe I should leave this up right here. Okay. Let's talk through how to solve numbers 1, 2, and 3. Hopefully, if you look here, number 1 looks an awful like number 1 up there for theorem 1112. So I'm going to go ahead and take 8 times 2.5 is equal to 2 times x. Okay? Just the cross product, or just multiplying those there just like they are up there. Okay? Go ahead and, I'm going to continue working on numbers 2 and 3 to make sure we set those up correctly. And then I'd like you to pause your computer and work through the algebra just to make sure that you know how to do that correctly. So in number 2, hopefully you recognize that number 2 looks an awful like number 2 up here. All right, and what that says is if you take the outer portion, the secant, times the whole length, which in this case will be 15, that will equal the outer portion times the whole length, which hopefully we're doing 4 plus x and not 4 times x. Okay? So again, just replicating what we see up in number 2. For number 3, we're going to go ahead and take the tangent line, which would be t, the tangent line, and square it. So y squared is equal to the outer portion, which is y, in this case it would be 2, times the whole length, which in this case is going to be 11. Okay? So pause your computer right now, take a moment, go ahead and solve those problems algebraically, and then we'll come back and talk about it. All right, if you solve this correctly, 8 times 2.5 is 20. Divide by 2, x will have to be a length of 10. Okay. Number 2, 5 times 15, that's 75. Distribute the 4 into the parentheses, 16 plus 4x. We subtract 16, we end up with 59. And then divide through by 4, I'm going to be close to 15, 14.75. Okay. From there, number 3, hopefully you have y squared equals 22. And then you can go ahead and square root that. Okay. And you cannot simplify radical 22. If you want to answer to the nearest tens place, we're looking at something like 4.7. Okay. So that's how you do those first 3. Pretty straightforward. Now, things do get a little bit more tricky both in setup and solution for numbers 4 and 5 here. Let me make this maybe a little bit bigger if I can. Have more space to work. Okay. Number 4, here's what I'd like you to do. Notice the radius is here, and we've done this on other problems before. We've rotated that radius. So this rotation, we can rotate it down and know that this length from here to here is going to be a length of 12. Okay. Over here, we know the entire length is 12, but this portion right here is x. So in order to figure out what this length is going to be, it's going to be 12 minus x. 12 minus x. Now, if it helps to redraw what we currently have there, you basically have a diameter, and then something right here like this. We have 8, we have 10, we have x, and then we have 12 plus 12 minus x, or 24 minus x. Okay, either way right there, that'd be fine. All right, now, to solve, we set up this looks a lot like number 1 again. So we're going to do 8 times 10 is equal to x times 24 minus x. Okay. Now, like I said, it gets a little tricky from here. So make sure you distribute your x correctly. And what you're going to notice here is that you now have a quadratic equation. Oh yeah, quadratic equation. So what do we do when we have quadratic equations? We try to get everything set equal to 0. And you would like your x squared to be positive. So I'm going to add x squared to both sides. I'm going to subtract 24x from both sides. And the 80 remains positive. Okay? Now from there, we're going to go ahead and factor this out. Okay, you might want to pause your computer right here and see if you can do it on your own. I think the factors are pretty clear. What are the factors of 80 that would have a sum or difference of 24? 20 and 4 would be 80. So I'm going to put, it doesn't matter where the 20 goes or the 4 goes. Okay. The last term is positive, so they're both positive, both negative. The middle term is negative, so they're both negative right there. Okay. So you end up with this from there. We know that either x minus 20 will equal 0 or x minus 4 equals 0. So either x equals 20 or x equals 4. Now, obviously we can't have two answers, and they're both positive. We talked before that you cannot have two positive, or that you can't have two answers, but we're always looking for the positive of the two. Well, in this case, they're both positive, so what do? Well, if you look up here, if this is 8 and this is 10, can this length be 20? Obviously not. Another way to justify that is this. If the radius is 12, can this portion of the radius be 20? Absolutely not. So we're going to get rid of that one, and that's going to be our length of x. Okay? So, looking at number 5, I would like you to go ahead and try to set this one up on your own. Pause your computer for a second. See if you can set it up on your own. The algebra is kind of tricky, I'm going to be honest with you, but the setup is not very hard. So take a moment and pause your computer. Okay. Hopefully you're looking at problem number 2 above and you're able to set it up. Here's how it should go. In number 2, it said that if we take the outer portion of the secant ray and multiply that by the entire ray, we should be able to get the outer portion of the secant ray times the entire portion of that ray. Okay? Now, you'll notice, if you've already started working on it, that this is going to end up being a quadratic. Z squared plus 12z is equal to 48. And hopefully you followed the same process, if you haven't already, of what we did before where we set it equal to 0. Now, in setting it equal to 0, I came up with a problem, okay? And I need to talk this out just to make sure I've done this correctly here. The factors of 48, 48 and 1, 24 and 2, 16 and 3, 12 and 4, 8 and 6. If you go down through any of those factors right there, none of them have a sum or difference of 12, okay? I have 16 and 8, sum and difference. Sum and difference, 14 and 2, 19 and 13, 22 and 26. So none of them have a sum or difference of 12. So what do I have to do? Well, this is where you have to do your quadratic formula. Now, quadratic formula. Now, I know some of you like this formula, some of you don't, but this is what you have to do. The formula, remember, negative b plus or minus radical b squared minus 4ac all over 2a. I'm going to get rid of that so you don't accidentally write down a 5 there. Okay? So, within my problem down here, a is 1, b is 12, and c is negative 48. Okay? So, if I plug that in, negative b, which would be negative 12, plus or minus radical b squared, which is 12 squared, minus 4ac, which is negative 48, all over 2a. Okay? Now, to simplify that up, let's see here. 12 squared is 144. Negative and a negative make a positive here and here. Negative and negative make positive. So we end up with 192. I think there, yeah, 192. So 144 and 192 gives you 336. So what we're looking at here is negative 12 plus or minus radical 336 over 2. Okay? Now, if you work that out in your calculator, again, you want to do this two different ways, if you don't remember. Negative 12 plus radical 336, whatever that is, divided by 2. And then it will be negative 12 minus radical 336 divided by 2. Okay? So you may want to pause your computer and go ahead and do that. When I typed that into my calculator, I got 3.2 and negative 15.2. Obviously, we cannot have a negative length, so we get rid of that, and that is going to be our answer. 3.2 is the approximate length of Z, and I think it even looks like it within the problem there. It makes sense. So, all right, I think you could probably do number 6 on your own. Okay, so take a minute here, do the setup, see if you can go ahead and solve for that. When you're done, go ahead and press play, and I'll talk you through the problem. All right, now this one looks like number 2 up above. You're looking up above on your paper there. So what I'm going to do is I'm going to figure out the sum of these two lengths first. Obviously this one's pretty easy. Okay, and this one over here, if you add up 7 plus 3, you get 10, so it's going to be y plus 10 right there. So it's going to be the outer portion times the whole length is equal to the outer portion times the whole length. Okay? And then we should be able to distribute and solve. Now, thank goodness, it's not going to be a quadratic, right? I mean, there's nothing squared, so it should be pretty simple. Not 8. 64 plus 8y is equal to 7y plus 70. Okay? If I subtract 64 from both sides, I'm going to get 6. If I subtract 7y from both sides, I'm going to get y. And there's your answer. Y should equal 6. Okay? So, online you also have your homework that I'd like you to complete for tomorrow. But I just wanted to make sure that you knew how to walk through some of those problems there. And especially reminding you how to do the algebra. It's been a little while since we've solved quadratics. So I hope you're good. If not, come and talk to me tomorrow. Otherwise, have a great night, and we will see you later. Goodbye.